return to the final law, the third law of thermodynamics. And in the discussion of the third law of thermodynamics, we look at the absolute temperature scale, because the absolute temperature scale yields the absolute value of entropy. Now that's remarkable because, in a sense, entropy is the most abstract of thermodynamic variables, and yet it's the only thermodynamic variable for which we have the ability to calculate its absolute value. And the fact that the third law of thermodynamics allows us to calculate the absolute value of entropy hinges on the fact that when we come to analyzing the entropy on the vertical axis against temperature on the horizontal axis, and we're going to achieve that increase in temperature by adding increments of heat, it turns out that the entropy at 0 Kelvin, at absolute zero, is identically equal to 0. This is a remarkable fact. So if we take, for example, a perfect crystal at absolute 0, the entropy is equal to 0, because any defect in that crystal turns out to increase the disorganization of the crystal and contribute a very small amount to the calculation of entropy for the structure of that crystal. Then as we proceed to increasing temperature, we increase entropy of that solid because we're contributing to the motion of those molecules that make up the solid. And as we contribute to the motion of those molecules, they become more and more disorganized. And as we are seeing this evolving relationship between increasing entropy and increasing disorganization, we see exactly why that's the case. Then we have the entropy of fusion, where we transition from a solid to a liquid. And then in the liquid phase, as we put more and more heat into the system, the relationship, the molecular motion, becomes more and more violent within that liquid, even though it's still in the liquid phase. And then finally, we can calculate the entropy of vaporization, going from the liquid to a gas, and that is an extremely large step, because if you look at gas molecules, they're moving around completely free of one another in a highly disorganized state. There's no intrinsic bonding in the structure. They're free to move as they will. But it's also true, even after we form the gas, as we increase the temperature, so too does the entropy increase. So the third law is disarmingly simple, but let's take a look at what it means quantitatively. Let's look at the entropy for a number of different substances. And in this case, watch the fact that we're calculating the absolute entropy, not a change in entropy, because we've pinned entropy to 0 at absolute 0. But let's take a look at the entropy of the different materials at T equals 298 Kelvin. The first thing we notice is that solid graphite, iron, sulfur, and so on have an extremely small entropy. So solids have small values of entropy. And the argument there is exactly the same one as we discussed as we increase the temperature of any compound, no matter what phase it's in, and that is that solids are locked down into a very strong bonding structure. They're highly organized, and so highly organized means low entropy. So let's just log that in. So highly organized is equivalent to low entropy. Now let's look at liquids. In particular, let's look at the conversion of liquid water to gas. And notice that the change in entropy is very large for the phase change of a liquid to a gas. And the logic flows in exactly the same way. A liquid, while the molecules are free to move past one another, they are bound in a structure which is broken when the liquid is vaporized into the gas phase. And the step of vaporizing, converting a liquid to a gas, dramatically increases the disorganization of the molecules within that system. So then we have a number of gas phase species. And here the interesting relationship is between the simplicity of the molecular structure and the entropy that's intrinsic to it. So if we take our old friend nitrogen and oxygen, and we increase the number of atoms in the molecular structure, we see that the entropy increases. So entropy increases with an increasing number of atoms within that molecular structure. But the argument is very similar. That is, if I have a larger and larger molecule, I have more and more degrees of freedom, of movement, of disorganization within that molecular structure. And we can see that, in fact, for gasoline, C8H18, even in the liquid phase, has a rather high entropy, 467 joules per mole Kelvin. So we can track then not only the fact that entropy increases in going from a solid to a liquid and from a liquid to a gas, but as we increase the temperature, the entropy increases uniformly. And also the other important factor is the number of atoms within the molecular structure. As the molecule gets larger and larger, its capability for disorganization increases, and therefore its entropy increases.